So then, let me show you the question first. Our computing problem number 8. Count binary digits. The title. Let me give you the problem. Given a positive decimal integer n, by default, so given integer, it's decimal, but here, why I emphasize decimal here, right? The reason is later, I will talk about binary. So that's the reason I mentioned this decimal first. Find the number of binary digits in its binary representation. We know binary digits, we usually call it bits, right? Bits. But here, binary digits, the meaning, original meaning, all right? Now, let us solve this problem. It looks not too hard, right? Given arbitrary positive integer n, find the number of binary digits or bits used in its binary representation. Right, so it's not hard. Remember our first introduction recursion problem, we start with factorial. That is not hard, that is very simple, but we can learn something useful from a simple example. Here, the similar situation, we have a lot of useful things we can learn. So let's do the analysis. All right. Here is the reference on our textbook. Okay. Analysis. So let's review the binary representation. In your discrete math, you learned binary representation, the standard binary representation. It's like this. Okay. N equals, then we have a sequence of bits. Here I arrange from the least significant bit to the most significant bit. V0, the least significant bit. V sub s, the most significant bit. All right, so that's the standard form. Obviously, V sub s cannot be 0. Otherwise, we reduce s by 1. Oh. Some noise, microphone. Let me see. Oh, Lubaba. So your microphone, you need to turn off. Okay. All right. So that means B sub s must be 1. Okay. If it cannot be 0, it can only be 1. All right. Then, now let us look at the answer in this representation. We can immediately get our answer expression, that is s plus 1. But the question is, here in your answer expression, you use s. And our given data, that is n. So when you have an expression not using the given number n, you need to do the conversion. You need to write this s plus 1 in terms of n. Because we do not know how large is s, right? So we need to write s in terms of n. Okay, all right. Still, we need to do some work. Otherwise, s plus 1, that's the answer. Not yet. You need to do some more work to find expression of S. Okay, yeah. Here, how to complete that step, that important step for this question. Here, I like to give you some insight how to get that step, the insight. So the insight here is because from this standard formula, this is the standard binary representation form, we do not feel we can see the answer easily. Yeah, it's still hard to see, you know, S expression in terms of M easily. Yeah. So we need to have some more friendly form. Yeah, this current form we feel not that friendly to discover expression for S. So we are looking for a different form, a more friendly form. Yeah. So here, the insight, how to find the insight. Here, I like to show you the typical way that we use to find the insight, all right, to discover that. That is, use a transformation to change the structure. Yeah. If you do not change the structure, it's hard to find that relationship. So now a typical way that we use in real world problem solving, we do transformation. For a given expression, we need to change its form. The original form does not reveal the insight. After we change the form, we can get the insight easier. That's the idea. Yeah. Here, let me show you the transformation part. All right. What is the transformation here? For this particular problem, division operation. The question, why division operation? Yeah. So let us observe this expression first, the structure. Okay, the right-hand side, sum of several terms. Okay, each term, so here, try to find some property. Each term is a multiple of power of 2. Okay, multiple of power of 2. Yeah. Then it is quite natural we can consider division by 2. Quite natural because each one power of 2. Consider the operation integer division by 2. Okay, yeah. When you do that, except the first term, yeah, because the first term, when you do division by 2, it may not be an integer, yeah, division by 2. Okay, the first one, 0 or 1, be 0. Only 2 possible values, 0 or 1. Okay, yeah. Other than the first term, all the remaining terms, if you do division by 2, they are all integers. Okay, but the first term, if it's 0, still 0 after division. If it's 1, the fractional part will be drop it because we just consider integer division. Okay, we drop the fractional part. Yeah. So with this observation, now let us do division by 2, both sides. Yeah. So the left-hand side, we need to take the floor function because we only want to get an integer expression. Okay, yeah. And right hand side, you can see B0 term is gone. Okay, no matter it's 0 or 1, after integer division by 2, that term is gone. Okay, all the remaining terms are still there. Yeah, but as for the power of 2, the exponent for each term, the exponent number is reduced by 1. Okay, yeah. So that is the structure change. Structure changes. So that is our transformation for this question. Okay, all right. Now you can see after we get this new expression, now we need to do some interpretation. Now, if this new expression can help us, get the answer easier. That's our goal. Find the answer easier. Okay, yeah, here. All right. Now let us go back to our recursive thinking last time. Here, we go back to the recursive thinking here. We need to use this recursive thinking here, all right? Yeah. Original problem here, original problem. Then after transformation, we get this problem different from original problem, but closely related. And we treat it as a subproblem. How about that? Subproblem. Because the problem size is smaller. Okay? The problem size is smaller than before, approximately 1/2 of the original size. Okay? So it's a subproblem. And you can see, in order to solve the original problem, we only need to solve a size reduced, a subproblem with size reduced. Okay, so here you can see we get the size reduction in this step. We just did size reduction. How about that? Size reduction. Okay, yeah. The smaller the size, the easier. And from the recursive thinking, when we can reduce the problem size, then we are very close to the recurrence relation to discover the recurrence relation. Here we are very close to that, right? Yeah, so it's actually in this recursive thinking, the critical step is discover some recurrence relation. That is the critical step. To discover an appropriate recurrence relation. Here, we want to discover that recurrence relation. Okay, all right. Before we can write it out, let us try to do some observation before we can write the recurrence relation clearly out. Okay, the observation. First, the least significant bit is removed. B0, the least significant. After division by 2, it is gone. Okay. It doesn't matter what the value it has, 0 or 1, it is gone. Okay. So that's the first observation. Okay. Second, the number of bits is reduced by 1. You just count the number of bits here. You have S bits, right? Little s bits. For the original question, you have S plus 1 bits. The difference is 1. Okay, so the number of bits is reduced by 1. The answer. Okay, yeah, the second observation. The third one, the problem size is reduced by half. Yeah, here, the problem size approximately, so we can treat it as half, okay, n over 2, floor function. Okay. With these 3 observations, now we can write the critical step, recurrence relation out easily. Okay, yeah, let us write it. Okay, let us use a special function to represent the number of bits for a given integer n. Okay, so that is here I call bin recursive binary. Okay, bin rec of n. Yeah, this function gives us the number of bits representation, but in recursive way. Okay, recursive way. So we get a recurrence relation. So the left-hand side, bin rec of n equals the right-hand side, we find the answer of the subproblem with half of the size. Okay, bin rec of floor function n over 2, approximately half of the size, but you need to add 1 because the difference is 1. So you add that 1 back to that subproblem answer, to the answer of that subproblem. Okay, yeah. After that, then you have this critical step, recurrence relation. We know how to solve the problem with given recurrence relation, right? Yeah, but we need to have a base case. Base case, just bin rec this function when n equals 1, the number of bits also 1. Okay, yeah. So we discovered this recurrence relation, so we can solve it. Okay, yeah. All right. Next step, we want to find the solution. We want to, so here, find the solution. Here the question is, because we can write a program to implement this recurrence relation with a function. That is very easy, right? Yeah. So here the question, yeah. To write a program to implement this recurrence relation is easy. Okay, yeah. Yeah. We do not need to, write a pseudocode here, no, because everyone can do it easily. Yeah. But here, let me give you some general problem-solving fact. Okay, problem-solving fact. Yeah. So that is, if you can find a formula, it is the best solution. Okay, yeah. So here, although we can do it in this way, all right, just write a program that given n, it will return the answer. So that is a solution. We have it. But another thing, because we want to find a better solution, right? We want to find a better solution. Here, I like to convey this point. That is, if we can find a formula for the solution, math formula for the solution, we just plug in a number, we do the calculation, we do not write a program, right? Because we have a formula, all right? Or we just write a program to evaluate the value using this formula. That will be much faster than your, program implementation from the recurrence relation directly, because you need to do a lot of recursion, right? In my formula, if I have a formula when I plug in, I do not need to do recursion, right? I just do calculation, simple calculation. Yeah. So that is the, reason I say, if you can find a formula, it is the best solution. It is much better, much faster than your, recursive implementation. Here we want to do that. Here we want to find a math formula. All right, yep, okay, all right, so here. That means we want to solve this recurrence relation. Okay, we want to solve it. Yeah. All right. So when we solve it, so let us continue our analysis here. Look at this integer division, n over 2. That is a special division because the denominator is 2. So we can treat it as a shift operation, left shift operation. We move the decimal point, but here let's say the binary point, right? Okay, so we have some bits. Then point, okay, because the integer the point and the fractional, okay, the structure. But integer we drop the fractional part. Then division by 2, we just move this binary point one position to the left. And after we move, we drop the bit after the binary point. Okay, And the good thing is, this operation is very fast. You just move position, left shift, much faster than addition. Addition, you need to do a lot of operation, a lot of internal basic operations. And the moving binary point, left shift or right shift, extremely fast. Okay, so that kind of special integer division, very fast. Okay, all right. So then, it is faster than addition. Okay, all right. So then, for this question, the basic operation is addition. Every time we need to do addition. Although we do one shift operation, one addition. But we also know addition is slower. So we like to, slower means it takes more execution time. So we like to focus on the slower part, the costly part, addition. Here, let us use a function a of n to represent the number of additions when we do the calculation. Okay, yeah. All right. So the recurrence relation will be a of n equals a of flow function of n over 2 plus 1. That's our main recurrence relation, but we need a base case. A of 1 equals 1. Yeah. A of 1, some of you may argue, could be 0 because we do not need to do addition. Yeah, but here, in order to make it close to our original problem, yeah, we make it a 1 because it's not a big deal, right? Just one difference from 0 to 1. The good thing is if we solve this problem, then the solution is the same as the original problem, right? Because the structure is exactly the same. Okay, yeah. All right, so let's try to solve it. Here, I like to show you the logical thinking procedure or process in solving this recurrence relation. Yeah. First, it's non-trivial. We need to do a lot of work. Second, we can learn many useful things from this example. Okay. All right. How to handle the flow function? In order to solve this recurrence relation, we know the flow function part, we do not feel quite comfortable because it's hard to predict, right? The flow function, sometimes you drop the fractional part, sometimes you do not. So it looks like there is some uncertainty there. If there is some uncertainty, then we need to pay more effort to handle the uncertainty. Yeah. Here, the flow function is 1. Yeah. Let us look at the property for a flow function division by 2 flow function. When n is an even number, its value is m over 2, but when n is an odd function, it is n minus 1, parenthesis, over 2. Okay, yeah, it's simple. We cannot call this expression hard. It's simple, yeah. But there is some uncertainty. In our recurrence relation, if we want to find the exact formula, here, not approximate formula, we want to find exact formula, then that truncation part is not very friendly, all right? Yeah. For our problem solvers, not very friendly, okay? So we want to make it friendly, okay? Because it's not very friendly. Can we make it a little more friendly here? Because we can make friendly assumptions, right? Yeah, it's not friendly, we know, but can we make some friendly assumptions we need? Right? Yeah, here we will do that. Yeah. Because when we solve a problem, if it is hard, then we can consider simpler cases, right? Yeah. Remember we have an old strategy we used before. Try simpler cases first. Here, we start with simpler cases first. When we start, we do not consider relatively more complicated cases. We want to make our lives easier. So we only consider relatively simpler cases. Here, we do the same thing. Okay? Yeah. How do we make our life easier? So let us, start with this question. What do you wish to have? Yeah, because you have freedom, right? When you start, you have freedom to choose simpler cases. Here, we want to take advantage of that freedom to make our lives easier. All right, yeah. So let's apply that freedom. All right. From the original of this given recurrence relation. Yeah. Because we don't know what is the exact expression of that n/2 floor function. Yeah. So we want to make our lives easier. So we want to look at this. We wish n even. Can we do that? Because when n even, n/2, it's already integer, so we don't need that floor function. The floor function is gone. How about that? So here we make a wish. Yeah. We have that freedom to do that. So we assume n is even. How about that? Yeah. Okay. Yeah. Think about this thinking approach. Yeah. In this class, I will use this thinking process several times. Here it is the first time. Okay. So we take advantage of the freedom we have, and we make some reasonable assumptions to make our lives easier. So in this step, we wish n even. All right. After that, we need to move to the next step, right? Not done yet. Next step. So we need to this time continue n/2 floor function at the left-hand side because it's n already even. So the left-hand side, the floor function already gone. We don't need that floor function. It's gone. But right-hand side, this n/2, the floor function is still there, right? It cannot be removed. Even if n is an even function, n/4, we cannot say n/4 is another integer, right? You cannot say that. That means the floor function cannot be removed directly. Then let us apply our freedom another time. This time we wish n/2 is an even number. Then the second floor function can be removed, and so on. Okay, think about that. Yeah. Some of you may argue you make too many assumptions. Yeah. Let us assume we can do that. How about that? Yeah, we want to make our lives easier, so let us assume we can do that at this point. All right. So if you can keep doing things like this, keep making the wishes as many as we need, eventually we will have this assumption. Assume that n is power of 2. Then we can do division by 2 all the way to the bottom without any necessary floor function needed, right? Because when we do division by 2, we have integer result. Yeah. Before we reach 1. Yeah. When we reach 1, we're already at the bottom. So we don't worry about that. That's the base case. So that's fine. So we don't worry about the base case. Okay. So look at this. Yeah. We make this big assumption. Assume that n is power of 2. So then all floor functions all gone. Then we simplify the given problem significantly. No uncertainty, right? Yeah. So we have the confidence to solve that problem. So let us solve that version first. Okay. So next step, this time we assume n equals 2 to the kth power, power of 2. Okay. After this assumption, then, although k equals log base 2 of n, because later we need to write k in terms of n. So here, let us put it aside, put this expression k equals log base 2 of n aside. So later we may need to use it. Yeah. After that, our new recurrence relation becomes this one. Yeah, look at that. A of 2 to the k equals a of 2 to the k minus 1, parenthesis, and plus 1. Yeah. The good thing for the new recurrence relation, the floor function is gone. We never need to deal with the unfriendly floor function, right? It's a big improvement. Yeah. Next, let's solve the recurrence relation. So do the, work like this. Yeah. The first equation, yeah. Next one, we do division by 2, right? Division by 2, still good expression. Yeah. Another division by 2, and so on, until we reach the bottom, the base case. Yeah. Because this one is base case. So we can stop. A of 1 equals 1, base case. Okay, all right. Now, with this sequence of equations, we just add them up, and do cancellation as much as we can from both sides. This diagonal type cancellation. Same term, two different sides, so we can cancel them out. Another cancellation, and so on until the last one. Then let us put the remaining terms. What is a of 2 to the kth power? What is that? To do that, we need to count the number of equations. How many lines do we have? So here's the question. Yeah. Here, it's a place to do the counting. Yeah. Here, I like to show you the, simple counting technique. Although it's simple, but I'm afraid some of you may not be able to do that correctly. Although I introduced a method for this situation before, but some of you may not be able to memorize it. So I call it counting by reference. Find appropriate reference, one-to-one correspondence. Remember, I explained that before in our module 1, when we do the counting, count the number of additions we used at that time. Here, we need to do that. Okay. Our goal, we need to count the number of lines. But due to this ... we may not be able to keep track of all these lines, right? How do you keep track of all these lines with the, many lines skip it in the middle, right? To keep track, you need to find appropriate reference to help you keep track of it. Here, let me find a reference. Okay, simple reference. The first line, top line, can we connect to the exponent number k? we connect to K as a reference. Okay, the first line has one-to-one correspondence with the superscript K. The second line corresponds to K minus 1 and so on. How about that? Okay, the last line connects to that superscript 1. How about that? Is that one-to-one correspondence? Yes. Now, when you do the counting, you do not need to count the number of lines directly. Can you count the superscripts from 1, 2, 3, until the last one, K? To keep track of these consecutive integers, it's easy, right? When we do the counting, we count these numbers. How about that? K, that's K lines, right? So we can get our answers easily. 2 parentheses, A of 2 to the Kth equals K plus 1. Yeah, because this base case, this number equals 1. And there are K1s. So that's the K part. Okay, K plus 1, that is the answer, exact number. Okay, yeah, accurate. Yeah, no approximation here. Okay, yeah. Now, because this formula, this is the answer, but still not exactly what we need, because it's in terms of K. In terms of K. We want some expression in terms of M, not K. K we treat as the intermediate variable. So not original variable. We want to use the original variable. Okay, so we need to make the last step, conversion step. So that is the result, A of N equals 1 plus the K. Now we can use the, expression that we saved before, that is log base 2 of N. So that is the final expression. Yeah. So we found that. All right. But this expression only true for N equals power of 2 to the K. If N not equal to power of 2, this expression may not be correct. Okay? Yeah. Because obviously, we know log base 2, it's not necessarily an integer, right? Where N is not power of 2, the log base 2 expression, it's not an integer. But the left-hand side must be an integer, right? A of N must be an integer. Okay? Yeah. But right-hand side is not an integer. So definitely you cannot use this formula when N is not power of 2. Right? Not power of 2. So it is wrong. Okay? Yeah. But our goal, if you want to solve the problem completely, you have to find the formula where N is an arbitrary positive integer. So there is a gap, right? There is a huge gap. How can we bridge that gap? How can we, fix it, that gap? Okay, yeah. That's the next question. Yeah. Because we want to solve this problem completely. So we need to get the answer from power of 2 case to the general case. That's our next step, the general case. Okay, yeah. All right, yeah. So we need to continue the work, right? Continue the work, right? Yeah. So here, for the work to be continued, can we make a guess? Can we make a guess here? Yeah. Guess the answer. Yeah. Let's do this step. Yeah. Because remember, we have a guess and a verify strategy before. If you can make a good guess, then later we can verify if our guess is correct or not. Yeah. So the next step, we like to apply that guess and verify strategy. Okay. Yeah. All right. So let's make a guess. Yeah. Because although we know this expression is not quite right when we move from n is power of 2 to the general n, it may not be exact like this, but can we make some modification to make it close to the correct answer? Yeah. So that's what we like to do here. All right. Make a guess. Yeah. We know log base 2 of n is not an integer expression in general. How can we convert it to integer expression? Is there a simple way to convert a non-integer expression to integer expression in a simple, easy way? Such way, yeah, we have seen it before. Okay, the guess, use the floor function. How about that? If you put a floor function on log base 2 of n, now it becomes an integer expression, right? For any positive integer n, this is an integer expression. But we don't know if it's correct or not, right? This is our reasonable guess, but we don't know if it is a correct guess or not, okay? And then there is another question, why you do not use the ceiling function. Here, because ceiling function also gives us integer expression, right? Why you do not use 1 plus the ceiling function of log base 2 of n? You use the floor function. We know these two are two different expressions. To answer this question, that's easy. You just try some simple numbers. Try n equals 3. Okay, yeah. We use floor function f of 3 equals 1 plus 1, that's 2. Okay, but if you use the ceiling function, the version, you will get 3, right? 2 or 3. Okay, yeah. But 3, yeah, look at that. If you count the bits, 3, that's 1, 1, right? 1, 1, 2 bits. Okay, yeah. But 3, not 3 bits, 2 bits. So that's why we take, floor function version. We do not take the ceiling function version. Okay, yeah. We just do some simple experiment. Yeah, yeah. You may argue, so A means the non-borough addition, right? Yeah, but we also know because the recurrence relation is exactly the same as our original recurrence relation. So the meaning the same. Okay, yeah. So that's why we can use this simple example for testing, for checking. Okay, all right. Yeah. Then, so here we know this is the best guess we can make. That's the best guess, right? Yeah. But the unknown part is we do not know if it is correct or not. So the remaining step, we need to verify it. We need to verify it to make sure it is 100% correct. then we can say we solve this problem completely. Okay, yeah. But that part, verification part, is pretty hard, so I delay it a little bit. Yeah. Later I will come back to solve it. Yeah. But I like to move to the next problem. Yeah. So we can move a little faster. After I complete next problem, then I come back for this one. All right. Yeah. So otherwise, we will spend too much time on one particular problem. Okay. All right. Yeah. So let me move to another problem, B.2, variable size reduction. Another important case for problem size reduction. But this time, the pattern, the reduction pattern is quite different. Variable size, every time the size of the problem reduced can vary. Sometimes larger, sometimes smaller. Yeah. Another interesting case. Yeah. So let's take a look at this case. Yeah. All right. First, let's look at our computing problem number 9, greatest common divisor. Yeah. You are familiar with this problem. Okay. Yeah. In your middle school, all students should learn how to find the greatest common divisor of two given positive integers. Yeah. Here we look at that question another time, but with some higher level understanding. Okay. Yeah. Because in your middle school, you do not know recursive algorithms, right? Nobody knows recursive algorithm in middle school. All right. Yeah. So here, let us use our new viewpoint to understand this question. Given two non-negative integers, here non-necessarily positive, we allow m or n to be 0. So two non-negative integers m and n, but now both 0. Now, we do not allow n and m both 0. Why? I will explain later. Okay. Yeah. The reason is quite simple, straightforward. Yeah, but later we will come back to answer this question. Why not both 0? Okay. Yeah. Question. Find their greatest common divisor, and here we use the function called a GCD function, 2 parameters m, n. That's the question, how to calculate. Okay, yeah. When we start, here the reference in our textbook. Now, but here I like to go back to the middle school procedure first. In the middle school, how do we find the answer? Yeah, step 1, step by step. Step 1, find the prime factorization of n. Okay, the first integer m. Yeah. Step 2, find the prime factorization of n. Okay, yeah. After that, step 3, find all the common prime factors between m and n. Yeah, by your eye observation. Okay, all right. Then the last step, compute the product of all the common prime factors. Yeah. Actually, each factor has a power of a prime number. Okay, power. Yeah, prime. Yeah. I hope you still remember the meaning of prime. Okay. the prime here. Yeah. Let us just review a little bit. The first prime is 2, not 1. Okay, we do not treat 1 as a prime. 1 is not a prime. Okay, the smallest prime is 2. Yeah. So its meaning is the only positive divisors it has is 1 and itself. Okay, 1, 2, only positive divisors. We do not count negative divisors. Okay, all right. 3, 1 and 3, you do not have any other positive divisor. 4 is not. 4, you have 2. Other than 1 and 4, you have 2 positive divisor. All right. So 5, 7, and so on. Okay. Yeah. So the prime numbers. All right. Yeah. So then the prime factorization, assume you know how to do prime factorization. Right. Assume, you know how to do prime factorization. Later we will talk about this prime factorization. Okay. All right. So here you can see this method relies on prime factorization, or the main step is the prime factorization. Otherwise, without using prime factorization, you cannot find the answer using, here I talk about this procedure. All right. Let us do a simple example here. GCD of 60 and 24. First, let us do prime factorization. 60 equals 2 squared times 3 times 5. 24 equals 2 cubed times 3. Then let us do observation to get the largest prime, power of prime common factor. From 2 squared and 2 cubed, the largest common factor as a power of 2, that's 2 squared. 3 and 3, the largest one, just 3. Then we do multiplication, we get 12. So the answer is 12. That's the middle school procedure. All right. It looks simple, pretty simple. All right. Yeah. But the question, prime factorization. All right. So the question is, can you answer this question? How hard is the prime factorization? How hard? Here it's not hard, right? Here, why here not hard? Because these numbers, we only do prime factorization on small numbers or relatively small numbers. Can you imagine you may need to do prime factorization on large numbers? Think about that. Think about. Think about this. You need to do prime factorization on very large integers. Okay. In the middle school, you never need to think about it, right? Because you do not need to do that. Okay. But here, we need to consider this question in the real world. Now, because in the real world, this is a serious problem. Okay, real world. And people may need to do prime factorization on huge integers. How large? Yeah. Here, when I talk about very large integers, think about how large, right? Because you need to have some idea on how large are these integers. Okay? Yeah. Here, let me give you some simple example. How large? 1,000 digits. As an example. One integer, it has 1,000 digits. Think about how large it is. Okay? You can use supercomputer. You're allowed to use supercomputer. Even that, supercomputer. Can you imagine how slow to do the prime factorization in this 1,000 digits? The current technology, based on our impression, the current technology, the computing power is so advanced, right? Now it's the AI era, right? We're already in AI era. So the computing power that we have, I refer to as human, okay? The computing power that we have is huge, right? Yeah. Even that, to do prime factorization for this kind of large numbers. Yeah. Let me use some conservative estimate. Do some conservative estimate. Months, how about that? Yeah. What I mean conservative, I do not say years, all right? So that's why I use months. That's my conservative estimate. Months to get an answer. Now you can imagine how fast it is. The calculation, okay, yeah, supercomputer, okay, and then many supercomputers, okay, but still in the category of several months, not years, not lifetime, yeah, because the old time, the computer technology was not very advanced, yeah, then, you know, years and a lifetime. But now the computer technology already is so advanced, but still we need several months computation time. Think about that. So that tells us one thing. This procedure for large integers, not good. Not good for, too slow for large integers. Right? If it's not good for large integers, that means we have to change. We have to find a different algorithm that is fast for large integers, for, you know, thousands of digits, even for that large integers, we can get answers immediately. So our question, all right. Yeah, so here, our goal. So here you can imagine the goal we want to have. We want to find GCD of m and n, but both numbers in thousands digits. Okay, yeah, but we want to get an answer. Get the answer immediately. That's the goal. Okay, get the answer immediately. Okay, we do not want to wait several months. So nobody wants to wait several months. So a completely new algorithm is needed to find such lightning fast. So the algorithm is lightning fast. Is that possible? Yes, it's possible. Yeah. Just today, we do not have time to learn that algorithm, but next time we have the time to learn that algorithm, lightning fast algorithm. Okay, yeah. And for this question, actually, I'm thinking about a programming project. Yeah, but because for the programming projects, we may need to do comparisons. Yeah, one, we need to do prime factorization. Another, the lightning fast algorithm to do comparisons. Yeah, but still, I haven't decided. Yeah, still, it's an open question for me. Yeah, so if I give it as an optional project or not. Okay, all right. So we reached the end of the class today. Yeah, so let me stop right here. But the remaining part still, we have a lot of things. One, some lightning fast algorithm, and another one, remember the general case for the counting bits problem. So those two topics, I feel I need a whole class session next time to complete those two topics. All right, so that's it.